Good evening.
Good evening, ma'am.
So, today we will be talking about voltammetry. Voltammetry is an important part in electroanalytical chemistry. We will discuss the various details of voltammetry, the various electrodes used, the different methods in voltammetry. We'll also discuss the types of current that is used here, and we'll also find out the practical applications of voltammetry in various qualitative and quantitative analysis of samples. So before going into the details of voltammetry, we should start we should with understand what are electrodes, the various types of electrodes that are used here, and the basic working principle of a voltmeter. So the various working electrodes that are used in voltammetry are also discussed here. So we will gradually go to that. And so the various methods that have been applied to the terms voltammetry and particularly polarography in a broader sense, since both are quite similar to each other. So well, voltammetry is particularly used for quantitative analysis of trace metals at the micro level. It is also versatile for research in various for redox purposes. It is useful for electron transfer mechanisms. It is also used for adsorption processes and production of new types of materials, or such as batteries that can store large quantities of energy, that is mostly for storage purposes. So, and more recently voltammetry has also been used for the production of pharmaceutical materials that involve by the green synthesis method. So here in figure 7.1, some of the common types of microelectrodes have been given. The figure, if we look into this is a disc electrode in 7a. It is generally called as a disc electrode. This in figure b, this is a mercury drop electrode, that is the DME, that is usually it is referred to as DME, the dropping mercury electrode. The mercury drop is present at the end here. Then figure C, it represents a dropping mercury electrode, and at figure D, it represents a static mercury dropping electrode. So some common voltammetric methods that have been used, that are commonly being used, first that include the use of direct current, that is called as DC polarography, linear sweep voltammetry, sampled DC polarography, and hydrodynamic voltammetry. Then, in some cases, pulsed methods are also used, and they are mostly called as normal pulse voltammetry, differential pulsed voltammetry, square wave voltammetry, and cyclic voltammetry. Now, voltammetry is also carried out by stripping method, and that is like anodic stripping voltammetry, cathodic stripping voltammetry, and adsorptive stripping voltammetry. In place of direct current methods, voltammetry has also been performed by using alternating current methods. So we'll first discuss the direct methods, that is, those employ the direct current. So first, we'll first start with the direct current voltammetry, that is linear sweep voltammetry that uses direct current. Here in linear sweep voltammetry, this is one of the simplest type of voltammetry that was initially developed. In this technique, the potential of the working electrode is first varied as a function of time. So as with the time varies, the current response is further recorded. So herein the scan rate is very low, and the movement, and this is always proceeds at a very lower space. So if we consider the equation, that is one electron reduction equation that is given here and that obeys Nernst equation, here E represents the potential of the working electrode and E0 is the standard reduction potential. Now if this solution containing only A is taken and the potential is applied of, let us say, 200 MV, then a very minute amount of current will flow to convert it into A to B. So the Nernst equation just is obeyed at the surface. The amount of current further increases as the potential approaches the standard value E0. That is, when E becomes equal to E0, the concentration of B is equal to A at the electrode surface. So that means that at E0, half of the total of A reaching the electrode is converted to B, so that the current is in its halfway towards limiting value. So here in figure 7.2, a normal DC polarography graph has been plotted here. As we can see, in the y-axis, the potential is taken, and in the x-axis, the time is represented. This potential, the versus time graph, it measures the amount of current changes with respect to time. Now, an important feature of this technique is that the large change in the slope that occurs around the E0, the value of the potential which corresponds to the point exactly where half of the total current is known, is called as the halfway potential. That is, and it is represented as E half. And this E half has been known to be widely used in qualitative analysis of various types of unknown species. So from the above discussion, we find that the difference, the sum of the migration current plus sum of residual current and diffusion current, that is id, is directly proportional to the concentration of the analyte, and this is used for analytical determination. That is id, the differential current or the diffusion current, id is equal to k into ca, where k is a constant and ca represents the concentration of the analyte. So this, the figure 7.3, it represents a simple linear sweep voltammogram of current versus potential, and this is called as LSV, of current versus potential voltammogram. The polarographic determinations can be achieved if we further increase the current value and we record the change in potential. So these modifications further the improved in the ratio of IF by IC, that is the Faradic current. If we increase the value of Faraday current and the condenser current, with this change will give has given rise to certain modifications in the LSV, and these changes gave rise to other voltammogram methods like the sampled DC polarography and the pulse polarography. So, with these modifications and the development of new methods, we came across the new novel development called as sampled DC polarography. Now here in this technique, instead of recording the current continuously, it is just pulsed, sampled for 5 milliseconds just before the drop falls. So now in between these time periods, the recorder maintains its last current and it holds the value of this last current in the circuit. So the major advantage of this process of or this current sampling is that it reduces the fluctuations in the current, and it prevents the fluctuations which ultimately affects the graph and the subsequent voltammogram. So if we look into the figure 7.3, it is seen that the current near the end of the life drop is nearly constant here. It remains constant at the end of the voltammogram. So, and that it is only measured in the current sample technique, and we find a very smooth curve for this. So LSV in the solution, in which the solution or electrode is kept in motion, is called as hydrodynamic voltammetry. So linear, this sample DC polarography, it is where the electrode is kept in motion, is generally called as hydrodynamic voltammetry. So we'll now discuss the details of hydrodynamic voltammetry. So here in hydrodynamic voltammetry, the current, as we know, is measured as a function of the potential applied to a solid working electrode which is kept in a stirring solution. Now, as the name implies, it is dynamic in nature. So the electrode is kept in a solution and it is stirred. So the linear scan profiles are used while the solution is in motion towards the electrode. So, and the scan is made when the solution is still continuously stirring. Here in hydrodynamic voltammetry, the cell has three electrodes. That is the working electrode, which is usually the mercury electrode, the reference electrode, that is the SCE, standard calomel electrode, and a counter electrode, and mostly it is the platinum coil. The current here, it passes between the working electrode and the counter electrode, that is the platinum coil. The electroactive substances that undergo the reactions at the microelectrode, they are brought to the electrode by three processes, that is by the migration of the charged ions, by the convection resulting from the stirring motion, and the diffusion of the ions due to the concentration gradient that establishes between the near the electrodes. So that is, the current is proportional to the concentration of electroactive substance. It is given by this formula, that is IL is equal to NFAD by delta into Ca. This IL is called as limiting current. The N, it represents the number of electrons, F is the Faraday constant, A is the area of the electrode, D represents the diffusion coefficient of the analyte, Ca represents the concentration of the analyte, and delta is equal to the thickness of the non-square. The stripping, here the stripping is accomplished where the magnetic stirrer is used. However, but in some, when at a constant speed the stirring is done, the obtained voltammogram and the current voltage plot here is characterized by an initial residual current and the potential till E half is reached. At this value of potential, the ions reaching the electrode discharge immediately, and thus the concentration in the diffusion layer remains nil. Now, the continuous flowing of electrons of ions into the diffusion layer, it maintains a constant current throughout the process. So, another way of carrying out this hydrodynamic voltammetry is that it involves the flowing of the analyte solution through a tube in which the microelectrode is fixed. This technique is the voltammetric detector in HPLC. So, in hydrodynamic voltammetry, two types of processes can be accomplished. Either the solution is stirred, or in the other way, the analyte solution is passed through a tube in which the micro electrode is fixed and the solution outside is stirred. So this is particularly what happens in an voltammetric detector, particularly in HPLC. Now, some important applications have been the detection and determination of oxygen and chemical species like glucose and other carbohydrates. This detector has also been used in electrochemistry and determination of other endpoints in volumetric titrations. Now, this is about direct methods in voltammetry. Now, coming to the pulsed methods in voltammetry. So, here, voltammetry, in this case, as the name implies, they are pulsed in nature. So, the sensitivity of this method is very large, and so based on this, the current in these methods is measured at a time when the difference between the Faraday current and the charging current is very large. Particularly, the pulsed methods, they are used in four cases and they are named as normal pulse voltammetry or polarography. This is usually called as NPP, differential pulse voltammetry, that is DPP, or square wave voltammetry, and the last one is the most commonly used cyclic voltammetry. So we'll discuss these methods one by one in details. Now, starting with normal pulse voltammetry or polarography, this is NPP. Here, the potential is altered by using a square wave potential pulses, and it is applied briefly before each current measurement. The data here that it has almost the shape of a linear sweep voltammogram, and the sensitivity is increased here. The dropping mercury electrode, it is held at the initial position unless there are some time left for before the time of the drop. Thus, very electrolysis and depletion occurs in this process, and the current is measured with great precision. Each new drop that is stepped into a greater potential, and it is measured after giving a delay of a very few minutes, very few microseconds. A sensitivity improvement has also been observed of almost 3 times in NPP. So this is almost the voltammogram obtained here is almost similar to that of a LSV, and it is high more sensitive than a normal LSV. So now coming to differential pulsed polarography. So here a greater improvement has been reached by using the waveform as it is shown in figure 7.6. These are some of the basic parameters that is shown in different voltammetric or polarographic techniques. So in particularly in differential pulsed polarography, the current is measured twice during the lifetime of each drop. Just before the drop, the pulse, and the second one just before the drop falls. In both the cases, the current is measured twice. The difference in the current is then plotted, which results in the voltammogram. The top of the peak, it corresponds to the E half, and the total height of the peak, it depends upon the concentration of the analyte that is used. The peak current in differential pulsed voltammetry, it increases linearly with the concentration of the analyte. So it also increases with the amplitude of the pulse. And in actual practices, amplitudes greater than 100 MV are not used because a value of greater than 100 MB, they broaden the peak and the resolution is also decreased. Now, if we look into figure 7.6, the NPP or normal pulsed polarography, the applied potential looks like this, and the current response is in the form of a this. For it here, now coming to the higher. So in DPP, as the figure it is shown here, the E versus T plot is shown here, and this is how the voltammogram looks like. And the figure 7.7, it shows the pulse application measuring procedure and current potential curves for both NPP and DPP. Figure A represents how the variation of a curve of determination of E half from figure 7A, 7.7a, it is for normal pulse voltammetry, and in figure 7B, it shows how to measure the E half and ID for differential pulse voltammetry. So the higher detection in DPP is due to the superior discrimination against the charging content and the Faraday current. The peak current in DPP is given by this value. So here that is represented in equation 7.3. So the detection limit for by this technique is similar to square wave polarography, and it is lies in the range of 10 to the power minus 7 to 10 to the power minus 8 moles per dm cube. However, for irreversible reaction, it is lowered. So now coming to square wave polarography or voltammetry. Here, as we can see in figure 7.6, a square wave voltammetry or polarography, it shows the figure like this, and the voltammogram looks like this. So we have a staircase in nature. The square wave polarography, it is a highly sensitive technique. It occurs with great speed and it has a very minute detection unit. The entire voltammogram can be obtained in less than 10 milliseconds. It has also put the power waveform is also similar to that of DPP, and it has also been used with DME and HMD. The excitation signal has been obtained by superimposing the pulse shown to similar to that of a staircase signal. For reversible reactions, a larger pulse is used so that its size is great enough for the oxidation product that is formed in the forward reaction and occurs during the reverse phase. Here, the in SVV. In SWV, it is possible to increase the precision of the analysis by signal averaging data from several voltammetric scans. The detection has also been reported to be in the range of 10 to the power minus 7 to 10 to the power minus 8 molar. The peak current in the technique is given as IP, that is the peak current is equal to Kn square d half del Ea by Ca. So IP is the peak current, K is the constant, N is equal to number of electrons involved in the electrochemical process, D is equal to the diffusion coefficient of the analyte, delta Ea is the amplitude of the pulse, and Ca is the concentration of the analyte. So using this equation, the peak per current can be calculated in the case of SWV. Now coming to cyclometry, cyclic voltammetry. Cyclic voltammetry or CV, it is one of the most commonly used electrochemical techniques for the study of various electroactive species in chemistry. The effectiveness of cyclic voltammetry, it particularly comes out from the fact that it rapidly observes the redox behavior over a wide range of potential. Here the voltammogram that is obtained is similar to that of a conventional spectrum, and it also conveys the information about the redox reactions in the form of a energy scan. So in spite of its wide application, however, certain sometimes CV is not well understood, such as compared to other techniques such as spectroscopy and chromatography. But still, CV is one of the most crucial factors while we consider redox reactions. Now, figure 7.8, it shows a typical cyclic voltammogram. The fundamentals of CV consists of cycling the potential of an electrode that is immersed in an unstirred solution of an electroactive species, and then finally the resulting current is measured. The potential of the working electrode is controlled versus a reference electrode such as a SCE or a silver chloride electrode. The controlling potential which is applied across these two electrodes, it is considered as the excitation signal. The excitation signal for CV is a linear potential with a triangular waveform as it is shown in figure 7.3. Here we obtain a triangular waveform. This triangular potential excitation signal, it sweeps the potential of the electron between two values, that is called as the switching potentials. The excitation signal in figure 7.9 causes the first potential to scan from cycle 1 to finally to cycle 2. The scan rate as reflected by the slope has been shown here. A second cycle, this represents the first cycle and this is the second cycle. So the cyclic voltammogram is obtained by measuring the current at the working electrode during the scanning process. The current can be considered the response signal to the potential excitation signal. Actually the voltammogram displays current in the vertical axis versus the potential in the horizontal axis. Now, since the potential it varies linearly with time, as it varies linearly with time, so as the current, it varies linearly with time. The horizontal axis can also be thought of like a time axis. That is, the x-axis can sometimes be considered as a time axis. Now, this has been useful for understanding of various redox reactions. Now, when we look at to a typical cyclic voltammogram that is given in figure 7.10, in the platinum here in figure 7.10, it represents a cyclic voltammogram of potassium ferrocyanide in 1 molar Kn potassium nitrate. So here this is how a typical cyclic voltammogram here it looks like. In a platinum working electrode in a solution that contains 6 millimolar of potassium ferrocyanide as the electrospecies in a 1 molar of KNO3 that acts as the supporting electrolyte. Here the potential excitation signal used to obtain the voltammogram in figure 7.59, but with the negative switching of this here, as we look into when the potential first, the potential initial potential is applied and it is chosen in such a way so as to avoid the electrolysis of the ferricyanide ion when the electrode is switched on. The potential is then scanned negatively, that is called as the forward scan. When the potential is sufficiently negative to reduce FeCN6 3 minus, the cathodic current is indicated due to the electrode process. So here FeCN6 3 minus undergoes reduction to form FeCN6 4 minus. The electrode is now sufficiently strong reductant to reduce the ferricyanide to the ferrocyanide. The cathodic current it increases rapidly until the concentration of FeCN6 3 minus at the electrode decreases totally, resulting to current peak, that is D. The current it follows then decays and the electrode is depleted due to the electrolytic conversion of FeCN6 3 minus to FeCN6 4 minus. Now the scan direction is then switched to positive for the reverse scan. So once after the completion of this process, the scan is reversed. However, but the potential is still sufficiently negative to reduce FeCN6 3 minus. So the cathodic current it continues even though the scan is now in the positive direction. So when the electrode becomes sufficiently strong, that is it is has now converted to FeCN6 4 minus, then the following oxidation process can occur, that is FeCN6 4 minus it gets converted to FeCN6 3 minus, and this causes the anodic current. The anodic current it increases rapidly until all the FeCN6 4 minus is reduced, and then it resulting from the current to peak. Now the current then decays as the solution around the electrode is depleted of the FeCN6 4 minus. The first cycle is completed when the potential until so this first cycle it is completed until all the potential of the positive comes back to approximately 0.40 volt, as it is suitable initial potential in the reduction of FeCN6 3 minus. Then this process it also avoids the electrolysis of the FeCN6 3 minus. However, in the forward scan, the FeCN6 4 minus that is electrochemically generated is also indicated, and the reverse scan that is FeCN6 4 minus oxidized back to FeCN6 3 minus is indicated by the anodic current. So this is from the voltammogram. If we look into the voltammogram of 7.10, both the anodic current and the cathodic current has been clearly mentioned. Now applying the Nernst equation, the potential excitation it depends on the ratio of the converting species at the electrode surface, and applying the Nernst equation, so we can this is the whole Nernst equation applied for the cyclic voltammetry of potassium ferrocyanide in mark KNO3. So and this equation is applied. The important parameters that needs to be considered for a cyclic voltammogram are particularly the anodic peak current that is represented as IPA, the cathodic peak current IPC, anodic peak potential EPA, and the cathodic peak potential that is EPC. Now these parameters have been labeled in figure 7.10. Here is the figure. So here is the figure which shows all the this is EPA, this is EPC, cathodic peak potential. EPA is the anodic peak potential, IPA is the anodic peak current, and IPC is the cathodic peak current. So these are some of the important factors that need to be considered during the CV. So the method of measuring of the IP it involves particularly the extrapolation from the graph. So it is generally difficult for a very complicated systems, and that is why the peak current is described by RS equation, or we call it as Randall-Sevick equation for the forward cycle, and this is given the IP is given by this in equation 7.8, where IP represents the peak current, N is the electrons that is used in the reaction, A is the area of the electrode in centimeter square, D is the diffusion coefficient, and C0 is the concentration, and nu represents the scan rate. Now here we can see from this equation, we can see that IP is directly proportional to C0. If all the parameters are kept constant, IP is directly proportional to C0. The relationship to concentration is important in analytical applications and particularly in studies of electrode mechanism. So therefore, the value of IP and IPA and IPC, it should be identical for a simple reversible couple. So that is IPC by IPA should be 1, and according to equation 7.8, IP increases with nu to the power half. Hence, the ratio of peak currents can be significantly if they are affected by chemical reactions that happen at the electrode process. Now, a redox reaction in which both the species that are rapidly exchanged with the working electrode is called an electrochemically reversible couple. The formal reduction, that is E0 dash for a reversible couple, it is mostly centered between the potential electrode potential of peak A and EPC, that is E0 dash is given as EPA plus EPC by 2. The number of electrons that is transferred in the electrode reaction for a reversible process is generally given determined as delta EP is equal to EPA minus EPC, which is equal to 0.059 by N. So for a one electron process such as the reduction of FeCN63 minus to FeCN64 minus, it exhibits an EP del EP of 0.059 volt. Slow electron transfer, it occurs at the electrode surface, and the irreversibility causes the peak separation, that is delta E2 increase. So this is how we calculate the delta EP for a various reduction reactions. The electrochemical irreversibility, it is actually caused by slow electron exchange of the redox species within the electrode. So in all these cases, the electrochemical irreversibility is particularly characterized by a separation of a peak potential which is greater than that indicated by this equation. So it is also electrochemical irreversibility is also caused by slow exchange of electrons of the redox reactions within the working electrode. This process is said to be quasi-reversible if it is reversible at low rates but become irreversible at higher ones after having passed through a certain region, and that is why they are called as quasi-reversible in nature. This transition occurs when the relative rate of electron with respect to that of mass transport is insufficient to maintain the nonce equilibrium. So here in a quasi-reversible region, both the forward and the backward reactions make a significant contribution to the current that is observed. Now here in table 7.1, there has been certain tests to decide the reversibility of redox reaction by cyclic voltammetry. So these are the criteria for a reversible system. So if E is equal to EPA minus EPC, that is we have already known as 0.0591 by N, but the criteria for a quasi irreversible system, it increases as IP increases with new hub but not proportional to it, so there is no reversible peak. So these are certain diagnostic table that conditions that has been listed for better understanding of cyclic voltammetry. Now the most marked feature of a cyclic voltammogram that we have almost observed is a total irreversible system in the total absence of a peak. However, such peak it does not it occur on its own, therefore it could be due to the presence of some fast chemical reaction. Hence, so to actually gain the inside knowledge about the reactions in the redox reactions, apart from CV, other processes need to be studied. So in some cases, it has also been found that the anodic current is much low as compared to cathodic current. So this is because most of the time throughout the experiment, there is a concentration gradient between thus working between the species which drives the reduced species, and most of the reduced species they proceed in the forward reaction, therefore they again diffuse into the bulk solution, and there is difficulty in oxidation of these species, and hence the time scale of the cyclic experiment of the CV experiment, that is in the anodic process, is longer, and thus it gives a reduced peak current as compared to cathodic peak current. So this is one of the lacuna of cyclic voltammetry that is usually encountered. Now, coming to the instrumentation of cyclic voltammetry, so it requires a waveform generator to produce the excitation signal. Here, figure 7.11, it indicates the instrumentation for cyclic voltammetry. Here is a waveform generator that is used that is an excitation signal. It is used for production of that. A potentiostat is then applied. It requires a potentiostat to apply this signal to an electrochemical cell. Then it is connected to a after it is connected to an XY recorder or oscilloscope, that is usually called as, to them to display the voltammogram. The first three items, the waveform generator, potentiostat, they are usually incorporated into a single electronic device through modular instruments. The potentiostat, it ensures that a working electrode will not be influenced by the reactions which take place. The data may be obtained with very low recorder even at slow scans. This is a typical instrumentation of a cyclic voltammetry. However, modern potentiostat, they utilize a three electrode system as it has been shown here. The potentiostat, it applies the potential to the working electrode and the reference electrode. The working electrode is the electrode where the electrolysis occurs. The current required to sustain the electrolysis is provided with the help of an external or an auxiliary electrode. This arrangement prevents large current from passing through the reference so that the change in the potential could be observed. A normal polarographic cell is used in this technique. These cells usually consist of a glass container, and the reference electrode is a typically a silver chloride electrode or a saturated calomel electrode. They are have been mostly used in many cases. The auxiliary electrode is usually a platinum wire that is directly dipped into the solution. Since the limiting current in all the voltammetric techniques, it is temperature dependent. The cell is thermostated. So thin layer cells have been used and they have been recorded down to almost 60 microliters. So a large number of working electrodes have been used. The dropping mercury electrode in polarography and the hanging mercury drop electrode in cyclic voltammetry, they are commonly used. Particularly, a thin coat of mercury has been deposited on graphite to form the mercury film electrode. A significant but importance of using mercury is that it is good negative potential range. Solid electrodes like made up of platinum, gold, or carbon, they are also used in CV, and such electrodes have better positive potential range than mercury. So we can say that CV is becoming increasingly popular in all fields of analytical chemistry, and particularly in the case of redox reactions, to understand the various reducible and oxidized species that are present during a particular chemical reactions. So this is all about CV. Now coming to stripping methods. Stripping voltammetry is a very sensitive electrochemical technique that has been used for the quantitative analysis of analytes present in micro amounts, and basically two steps are involved in this technique. Here in stripping method, that is stripping voltammetry, first is the analyte of interest. It is electrochemically deposited on the working electrode by the controlled potential electrolysis. A controlled potential electrolysis, it means that the process is carried out at constant applied potential, and then in the second part, the a reverse potential seal or stripping seal is applied, in which the deposited analyte, it is removed from the electrolyte. The first step here, it actually it indicates the deposition, while the second step is the stripping step. So basically two steps are here important. One is the first one, which indicates electro deposition, and the second, which includes the removal or the stripping of the deposition from the electro surface. So based on this, there are three types of stripping voltammetry. First is the anodic stripping voltammetry, second is the cathodic stripping voltammetry, and the third is adsorptive stripping voltammetry. So we'll start with ASV, that is anodic stripping voltammetry. This has been technique has been used to determine very minute amount of metal ions by reduction to its metallic state. The microelectrode that is taken here, it behaves as a cathode during the deposition state and as an anode during the stripping step, while the analyte is being oxidized to its original form. So let us take the example of Cu2+. The deposition reaction at HMDE, it held that a cathodic potential is sufficient to first deposit the metal on the electrode, that is Cu2 plus plus 2 minus. It deposits the Cu on the electrode, where CuHg here it represents copper is deposited on the HMDE, that is the hanging mercury drop electrode. This step is basically a pre-concentration or the electrode deposition step. The solution is then stirred to electrolysis during the process to increase the rate of deposition. Near the end of the deposition time, the usually 1 to 30 minutes are taken. Mostly half an hour is used for the deposition process. After 30 minutes, in the second step, the potential is scanned and anodically towards more positive potential. When the potential turns out to be positive, the analyte that was deposited on the electrode, it is stripped from the electrode and it returns to its oxidized form, that is the CuHg, that is the copper which is amalgamated or which is present on the mercury. It comes to Cu2 plus, and the current during this step is monitored as a function of potential, giving rise to the voltammogram, the peak current of which is proportional to the analyte concentration. This technique is very sensitive to experimental conditions such as the size of the mercury drop, the deposition time, the rest time, the rate of stripping, and other factors. So if this is properly controlled, then this method is very sensitive and accurate, and it can be used for metals that form amalgams. Figure 7.12, it shows the details of a stripping voltammetry. Now, in anodic stripping voltammetry, the determination of the analyte is based on anodic dissolution. This process is followed by voltammetrically, and the peak current thus obtained, it is proportional to the potential scan rate or the scan rate of the surface area of the mercury film. In both the cases, the peak current IP is given by equation 7.14. So substituting the exact values, we can find out the peak current that is used. However, the peak current depends on the time of electrode deposition, and therefore it is proportional to the concentration of the electrolyte in the amalgam that is formed here, and it is indirectly proportional to the concentration of the analyte in the sample solution. The peak currents in this technique are linear function, and they have been used for determination of many metal ions even in trace quantities in environmental samples. Now coming to CSV, that is cathodic stripping voltammetry, it has been used for determination of anions that form insoluble mercury salts at the mercury surface or insoluble silver salts on a silver electrode. The experimental design is similar to that of ASB, however with slight modifications. Here the decomposition step, it involves the oxidation of the mercury electrode to Hg2 plus, which then reacts with the analyte to form an insoluble film at the surface. And seconds, then the decomposition step with Cl is given by that this 2Hg, it reacts with Cl forming Hg2Cl2. In the second step, that is the stripping state, this is followed by scanning cathodically towards a more negative potential, that is the reduction of Hg2 plus back to Hg and returning to the analyte solution, that is Hg2Cl2 is again converted to Hg and returned to the solution. Some of the analytes used by cathodic stripping voltammetry include the halides, sulfides, and mercaptans. The third part is adsorptive stripping voltammetry. Here, the analyte is adsorbed on the surface of the electrode, and there is no electrolysis step. And after complete deposition, the potential is scanned in either in anodic or in cathodic direction, depending on the type of the analyte that has been oxidized or reduced. The deposition step here, it amounts to the electrochemical deposition of the analyte, and it is and on the surface of the electrode that is used here. Some analytes that has been analyzed by adsorptive stripping voltammetry that include cocaine and testosterone. So now coming to alternating current methods, the voltammetry that uses alternating current methods. Here, the linear potential is modulated by a single wave voltage of a small altitude, which produces an alternating current. The size is determined by the direct potential applied, and which is greatest at the E half. The plot is here shown in figure 7.13 of here how it is a peak shaped alternative current polarogram has been represented in figure 7.13. The expression for peak current here is given as ip is equal to kn square e square ca, where ip is the peak current, k is equal to constant, and e represents the amplitude of the superimposed alternating current. The Ca is the concentration of the analyte, N is the number of electron, and F represents the frequency. Thus, the height of this polarographic peak can be used for the determination of the concentration of the analyte, which is quite similar to that in the DC polarographic method. The AC polarographic peak currents, they are widely dependent on the kinetics of the charge transfer reaction. Now, for reversible processes, the half width of the peak is equal to 90 by n, and which depends upon the number of electron as exchange, as a result for which the value of n will be narrower and the b will be broader in this process. AC polarographic determinations are limited to a sensitivity because of high capacitance current conductions, which is the main source of periodic charging and discharging of double layer. The above sensitivity of the reversible redox processes can be improved if the AC is measured at a particular phase shift with respect to the excitation signal. The first harmonic AC polarography, that is the AC1 polarography, the measurement of the harmonic of the AC resulting from second harmonic, it reduces the capacitance current contribution, and thus the sensitivity of the instrument is dropped. The market available instruments, they are mostly equipped for DC measurements. However, AC measurements are also available sometimes. Now, in figure 7.71, the basic instrumentation of voltammetry has been represented. The basic instrument, it consists of two major components. First is a normal 3 electrode polarograph, and the second is a linear scan voltage generator that gives different types of signals. The polarographic cell is made up of three electrodes that is dipped in a solution containing the electroactive species, and excess of inert electrolyte, which is called as a generally referred to as the supporting electrolyte. A working electrode is usually, which is a micro electrode, is taken whose potential is varied linearly with time. A reference electrode is taken that is normally a standard electrode whose potential is constant throughout the experiment. The counter electrode, which is mostly a platinum coil or a pool of mercury that just serves to conduct electricity from the source through the solution to the micro electrode, that is the working electrode. The potentiostat, it allows to impose the potential scanning between the working and reference electrodes, while the current flow through the circuit is recorded between the working and auxiliary electrodes. Now here, the the computer analyzer, it has been used as an integrated instrument. It can be assembled with a computer and other softwares to measure the scanning parameters of the potentiostatic analyzer and to check its correctness and accuracy, and it also handles the current potential output data. So with this, we complete the unit of voltammetry. So next we will start with polarography and amperometric titration. So before going to that, we'll just take a break of 5 minutes. So now coming to polarography and amperometric titrations. First we'll start with polarography. This method, polarography, was developed by Herovsky, and he won the Nobel Prize for the discovery of this technique. He initially it was one of the forms of voltammetric technique. Now then he recorded the current potential curve and he called them as polarograms. And then finally it was he introduced the term polarography. Now when we consider Ilkovic equation, the ID, that is the diffusion current, is proportional to concentration. That is, we know ID is equal to K into C. So particularly this, if any electroactive material is present in the solution, it is removed by interaction with complexes such as like EDTA is used for Zn2 plus determination. This is the fundamental principle of amperometric titrations, or what we call it as the polarographic titrations. The most metal ions, they are reducible at the dropping mercury electrode, and multi-component mixtures have often be analyzed by selecting an appropriate electrolyte. So by these processes, reducible anions such as BrO3 minus, IO3 minus, Cr2O7 minus, and nitrite NO2 minus, they can be determined using well buffered solutions. Now here, during the electrolysis process, the chemical reactions, they occur under the influence of a EMF at the electrodes immersed in solutions. Now the reactions occurring at these electrodes, that is the electrode reactions, they are characterized by the transfer of the electrons occurring between them. Because of this, the equality of the positive and negative ions, that is, they are unbalanced, but they are counteracted by oppositely directed movements. So, as a figure 8.1, as we can see, this current actually measures the movement of the electrons in the external circuit that connects the two electrodes. Therefore, the current is the result of the electrode reaction. The electrode at which reduction occurs is usually the cathode, and which the electrode oxidation occurs is usually the anode. The curve obtained by plotting the EMF applied to the cell against the applied current is the IE curve, or the current voltage curve, and it is usually represented by a polarogram as shown in figure 1.1. When the applied potential, it becomes equal to the decomposition potential of the electroactive species. Like for example, if we take Zn in this case, then the at the cathode the current starts increasing due to the following cathodic reaction, that is given as Zn2 plus, which takes up two electrons, and it forms ZnHg, that indicates zinc forms an amalgam with mercury. So as the potential of the dropping mercury electrode, that is the electrode that is used, is made more negative, then there is a further increase in current, which accordance with Ohm's law, and Zn2 plus is reduced. Now if you look into from point C to D, here in figure 8.1, if we look into point C to D, the current remains constant, which determines the rate of diffusion of the Zn2 plus ion from the bulk of solution to the electrode surface. Now the number of Zn2 plus ions that diffuses from the bulk to the electrode surface is equal to the number that is already deposited on the during the steady state of the reaction. So that is when before equilibrium, that is the rate of diffusion is equal to the rate of reduction. So when the applied potential, it exceeds the decomposition potential of the DME, it depolarizes the Zn2 plus, it forms Zno and forms an amalgam with the mercury, that is the with the DME electrode. So here the Nernst equation is applied in this case, which is given as E is equal to E0 plus 0.059 by 2. 2 indicates the valency of Zn and log of Zn2 plus. Now at point C, there is no longer current. The current, it in no longer it increases linearly, but it approaches a constant value to point D. So no increase is observed. even at higher cathode potential, until a second compound that is able to depolarize is present in the solution. So from C onwards, the DME becomes depolarized. Because of this polarized and depolarized of the electrode that is caused by the electrode reaction, this curve so obtained, that is in figure 1, this is called as a polarogram. Figure 8.1 is called as a typical polarogram. Now, the dropping mercury electrode, or the DME. The small dropping mercury electrode, it has a very fine bore ranging from 0.05 mm to 0.08 mm internal diameter, and it is almost appreciably 10 centimeter long. The of the mercury, it falls at a steady rate of 3 to 5 drops of second per drop, and it is adjusted accordingly. The current oscillates between a near zero value as the drop falls from the capillary to the maximum value. The DME method, it has several advantages. The surface area is reproducible with a given capillary. The constant renewal of the electrode, it eliminates the poisoning effects, it eliminates the presence of any impurities present. The large hydrogen over potential on mercury, it renders possible deposition of substances, as we can see it from the IE curves. Mercury forms amalgams, we know, with many metals. The diffusion current, it behaves steady, it assumes a steady value, and it is reproducible in nature. The surface area of the electrode, it can be calculated from the weight of the various drops. The dropping of mercury electrode has been very useful in the range of zero point 0.3 to -2 volt versus SCE. So here in figure 8.2, it shows a current oscillation with DME. Yeah, DME. Then migrating and limiting currents. So first is the limiting current. The limiting current, which is obtained in dropping mercury electrode, it is caused by the extreme concentration polarization, which results from the depletion of the concentration of the electrode deposited substances at the electrode due to surface electrode reaction. The reducible or oxidizable species that are supplied to the deleted region, they are at the two surfaces. A diffusive forces that is proportional to the concentration gradient at the electrode surface, and there is an electrical force that is proportional to the electrical potential between the surface and the solution. So the limiting current can be generally regarded as the sum of the diffusing current and the migrating current. So now the migration current. The migration current is due to the migration of the either the reduced species or the oxidized species, which is proportional to the electrical potential gradient at the electrode due to attraction. Unless this gradient is removed, this potential difference is removed, the limiting current cannot be proportional to the concentration of the electroactive species. Now, migrating current is usually eliminated by adding excess of a supporting electrolyte. Now, mostly they are potassium or sodium salts. The potassium salts, they cannot be discharged at cathode until the voltage becomes very large. The large number of potassium ions, they crowd the cathode and they ultimately restrict the potential gradient, so that they remain very close to the electrode surface. So as a result, there is no longer an electrostatic attraction between them to attract other ions from the solution. So under these circumstances, what happens is the limiting current is solely controlled by the diffusion of the electroactive species that we have taken under consideration. The migration current, it depends on the transference number of the reducible or oxidizable ion and the total current, and is given as Im, that is the migration current, is equal to Ti into IL, where Ti represents the number of the species and IL is the total limiting current. So here in table 8.1, the limiting current in solutions containing various concentrations of supporting electrolytes has been listed. From table 8.1, it says that the transference number of an ion decreased practically to zero in presence of almost 100 times of the supporting electrolyte, that is KNO3. So in most solution, almost all the current is carried through the cell by the potassium and nitrate ions. However, these are not reduced before the evolution of hydrogen. So migration current is practically eliminated by keeping the supporting electrolyte more than 100 times than the concentration of the reduced or oxidized species. Now coming to diffusion and residual currents. Diffusion current in the presence of excess of the electrolyte, that is when it is taken in huge excess like almost 100 times of the reduced or oxidizable species. So the electrical force on the reduced species or oxidized species is nullified, and therefore limiting current is just only it acts as a diffusing current. So Ilkovic, he examined the various factors that govern this process, and he deduced a theoretical equation given in equation 8.3. So here a constant 6.7 is present, which combines all the natural constants including Faraday and other factors. This is an important equation because it shows the linear dependence of ID, that is the diffusion current, on C, that is the concentration of the actual species, the reduced species or the oxidized species in solution. So, however, in actuality, the limiting current is not exactly the same as the diffusion current. But since the supporting electrolyte, which we have taken in high excess, that of the it contains impurities that sometimes result in the contribution of the formation of a very small current in addition to other currents, and this is known as the residual current. So, even in the absence of a very electroactive substance that has only the supporting electrolyte, a small current is always present in the solution, and which is called as a residual current. Now, the residual current is generally composed of two components. The first is reduction of trace impurities, which are present in large concentration of the supporting electrolyte, like mostly dissolved oxygen, traces of metal ions such as ferric iron, lead, arsenic, and the second component of residual component is the charging current or capacitive current, which is non-Faradic, and it is present whenever working electrode potential changes. So this small current that is observed from the supporting electrolyte solution is because of the continuous changing of the mercury drop. So since the mercury is covered with an electrical double layer, and it contributes to the small current in the residual current. So the residual current, it is responsible for determining the accuracy and sensitivity of various polarographic method at different concentrations. Even minus 5 molar, the residual current is larger than the Faraday current, and therefore these solutions are not very sensitive. Then there are various factors that influence the diffusion current. The first, there of the many factors, there are the major factors are the concentration of the electroactive substance, the dimensions of the capillary used, the pressure of the dropping mercury electrode, the temperature, the viscosity of the medium, the composition, and others. So first, now start coming to the influence of the concentration of electroactive substance. When we look into the Ilkovic equation, that is ID is equal to K into C, ID is the diffusion current. So there are instances where ID is not constant and the current is determined by rate of chemical reaction, that is called as catalytic kinetic currents, and sometimes the adsorption or of the electroactive substance or is electrode reaction result in the formation of other waves. So the concentration is also a factor that influences the diffusion current. The capillary characteristics and the factors that affect them. From Ilkovic equation, we know that diffusion current depends on M and T and are therefore affected by their variations. M is directly proportional and T is inversely proportional to the pressure on the mercury drop. Now, when all these factors are combined together, it has been found that ID by root H is equal to K dash. So here, first, we find that ID by KH is equal to K, where K is a constant. Now, any deviation from this indicates that the current must be partly or wholly governed by other processes than diffusion. So, this factor, the equation ID by root H is equal to K dash needs to be maintained. So effect of pressure, mercury pressure or MNT has been here represented in table 8.2. Then the influence of temperature on diffusion current. The change in temperature affects all values of the Ilkovic equation except the value of n, that is the number of electrons. The temperature coefficient of M is about 0.27% per degree. So the temperature coefficient is about very, when it is m t to the power 2 by 3 t to the power 1 by 6, almost accounts for 0.15% per degree. So combining all those the factors, it is advisable to keep the temperature constant within plus 0.5 degree. The temperature should be used within a standard deviation of plus minus zero point 0.5 degree. Then the solvent and the supporting electrolyte that influences the diffusion current. The diffusion current is very much dependent on the D, that is the viscosity of the medium. The ID, that is the diffusion current, decreases with increase in viscosity of the solution, as capital D, that is the diffusion coefficient, is inversely proportional to the viscosity of the medium. So when we consider Ilkovic equation, ID is proportional to eta to the power half. Now eta varies as the aqueous solution changes from non-aqueous medium. So changes in the composition of the supporting electrolyte by adding complexing ligands to the metal complex, and therefore they also shifts the value to more negative potential. Thus it is necessary to keep the concentration of every constituent of the supporting electrolyte within about plus minus 10% to measure for effective measure of ID. Then is the polarographic equation. So let us consider oxidant and a reductant, where the oxidant takes up n number of electrons to form a reductant. The electrode potential for such a reaction is given as E is equal to E0 plus RT by NF, ln activity of oxidant by activity of reductant. Now if we consider the in equation, if we rearranging this equation, we find that E is equal to E0 plus 0.059 by n log of concentration of oxidant by concentration of reductant, where 0 includes the, here E0, it indicates the standard EMF. Now putting all the values of Ilkovic equation in equation 8.6 and further substituting the values, similarly we find that I is equal to K2 into the concentration of the reductant. So if the reductant is soluble in water, it will diffuse from the surface of the electrode to the bulk of the solution. As the concentration of the reductant, it varies with the value of I, and hence the equation is further changed to E is equal to E half minus 0.059 by n log of I by ID minus I. The equation in 8.13 is termed as the equation of the polarographic wave, and it represents the potential as a function of current at any point on the polarographic wave. So the even the treatment of anodic waves remains the same. The equation here in 8.13 is the standard of wave polarographic wave equation. Now coming to E half and its effect on various complexing agents. Now E half is generally called as the half wave potential. So the electroactive material in polarography is particularly characterized by E half. Now under any set of conditions, each substance has its characteristic E half, which is the basis for various analysis. The E half is defined as the potential at which the current due to the redox process, either the reduction or the oxidation, is responsible for the wave is half as large on the plateau. The half potential is also dependent on electrode characteristics and concentration of the species, and therefore it also serves as a measure for qualitative identification or in qualitative analysis. Now, the influence of complexing agents. In the case of complexation of metals with a complexing agent, the electrons, the reaction can be written in two steps, and the E half for such a type of reaction can be given as E half is equal to E0 plus 0.059 by N log of K minus 0.059 N 59 by N log of XB minus, where P represents the coordination number of the complex and XB minus is the complexing agent. So P is determined, the coordination number, it is determined by taking the E half values with varying concentrations and by plotting a graph as shown in figure 8.5. So from the, if the graph we plot and we with a E half, the a line with a slope equivalent to minus P 0.0591 by N will be obtained, and from this plot we can find out the value of P, where P represents the coordination number of the complexing agent. Now once we know the value of P, then the E half can be determined from using equation 8.16. Now here table 8.13, it shows the few metal ions in complexing and non-complexing medium at DME. Then determination of N and reversibility. So when from equation, if we look into equation 8.13 here, that is the polarographic equation that we have studied. So here we find out that here we find out that when we plot a graph of log of I by ID minus I against the potential, applied potential, a straight line is obtained. The slope of this line will be equal to 0.0591 by N, from which N is calculated. Looking from the graph, if we look here, then here the N is calculated from figure 705, the log this graph, after we calculate the n value, if the value of n it is an integer, then we can know that the electrode reaction is responsible and the wave is reversible in nature. If the slope of the log plot is larger than expected n, or n is not an integer, then the wave is irreversible in nature. So this is how the value of n and the reversibility is known. The half-wave potential for reversible wave is easily found from a log point here as it is shown in figure 8.6 in the plot here. And another method to determine the reversibility of electrode reaction, which is simple and corresponds to 1 by 3 and 3 by 4 from the polarigram. So this means that at E1 by 4 for a reversible cathodic wave, this is given as E1 by 4 is equal to E half minus 0.0591 by n log 1 by 3, and E3 by 4 means that E3 by 4 minus E1 by 4 is equal to 0.0594 by 564 by n. Therefore, the value of E3 by 4 minus E1 by 4 is equal to minus 56.4 by mn, and for reversible it is plus 56.4 by n millivolt. So irreversible reactions, many electrode reactions are primarily or they are partially or totally irreversible in nature. The polarogram in these cases is less well defined. So the polarographic equation for such reactions is defined by equation 8.18, which is is equal to E half minus 0.591 by alpha into n into log I by ID minus I, where alpha represents the transfer coefficient and it accounts for the kinetics of the electrode. So even in such electrode process, the diffusion current is proportional to the concentration and therefore it is used in quantitative analysis. However, the E half here, it is slightly varies with concentration of the electroactive substance in solution. Now, there are other currents than diffusion current, and mostly these currents are called as kinetic currents, catalytic currents, and adsorption current. In kinetic currents, when some substances they are not electroactive in nature, but they are made electroactive due to some chemical reactions. The product here so formed, they undergo reduction or oxidation at DME. The height of the wave, it's determined by the rate of the chemical reaction. So the wave of this kind, they are called as kinetic waves, and the mechanisms are Y2O. In the forward reaction, the rate is given as Kf, and in the backward reaction, the rate is given as Kb. So where Kf and Kb, they are the first order rate constants for the forward and backward reaction. So the kinetic current, these are recognized here, is given by the equation Ik. K stands for the kinetic current, and this equation is used where the capital D is the diffusion coefficient for the species either Y or O. The kinetic currents are also recognized from M2 to the power 3 and T2 by 3, which does not vary with the height and is independent of H core. The kinetic currents, they are not much in practical use. Also, the possibility of impurity is very high. That is why the possibility of kinetic currents are much lesser. Now coming to catalytic currents, when an electroactive substance, they are reduced at the electrode given as O plus Ne forming R, and if the solution is contained in another substance Z which is not electroactive, then A is followed by this reaction R plus Z, K forward reaction forming O. Because of the regeneration of an electroactive species by this process, more and more O here is reduced. The process is continued until the applied voltage becomes negative and the plateau of O becomes a limit. The average catalytic current here is given by this. So by IC is equal to 493 N, and this equation in 8.23. So here it is important, this process, it needs the extremely low concentration of original electroactive substance can be measured by this process. Thus they are very useful for trace analysis of transition metal ions, and the catalytic currents, they are identified as IC. Then comes adsorption waves. Some electroactive species or their products, due to various types of oxidation or reduction, they are adsorbed on the surface of the mercury electrode and they give adsorption waves. That is, in the electrode reaction, O plus n number of electrons forming R. If the R is adsorbed at the mercury surface, the current obtained is very small, and that is called as the adsorption wave. And a single wave is obtained whose height is proportional to O. But after certain concentrations, when the surface of the drop is saturated with R, a second wave is observed. So this representation has been shown in figure 8.8. So from the time the normal appeared, the height of the adsorption, it remains constant. The total wave of the first and second together, they are proportional to O. So adsorption of this kind, they have been used in solution of thiols and other organic materials. These adsorption waves, they have been used for the calculation of the area of the adsorbed species, and they have been used from the equation that is given below, and this is particularly used for an adsorption wave, that is IE is equal to 13.66 n m 2 by 3 t minus 1 by 3 by capital A, where A represents the area that is covered by the adsorbed molecule. Now coming to polarographic maxima, if we look into this figure 8.9 here, so before going to that, let us understand that current voltage curves that are obtained at TME, they can be distorted. That is, the plateau can be reached easily as the applied potential is increased. Now, there has been certain abnormal increase in current, which we usually refer to as maxima, and they also vary in their shapes in the form of humps or other sharp peaks. So, gelatin is a widely used surfactant or an surface active reagent to prevent such streaming of the movement at the interface or during the polarographic measurement process. So gelatin, higher concentration of gelatin, it also suppresses the diffusion current. So triton X100 has also been used. In figure 8.9, the polarigram of 2.3 millimolar lead in presence of zero point 0.1 molar potassium chloride is used. Here is shown in figure A. Here in absence of a suppressor, whereas figure B denotes that the after addition of a surface active reagent, the intensity of the plot polarigram it decreases here between A and here it is B. The qualitative and quantitative polarographic analysis has been carried out mostly by matching the value of E half that is obtained during the experiment and that is reported in literature. It is also advisable to use the log plot for knowing the correct value of E half. So in table 8.4, the E half of some of the common ions have been listed, which shows its corresponding values, and E half of some of the anions have also been listed here. The quantitative polarographic analysis. Polarographic analysis can be used for detection of 10 to the power minus 3 to 10 to the power minus 5 molar concentrations of the electroactive substances. If the solutions they have more than one electroactive substances and their halfway potential in particularly for the supporting electrolyte differs by zero point 0.4 volt, then they can be determined. So if the halfway potential, that is the E half of two ions, are close, then various experimental devices have been employed, such as precipitation of one, that is for lead and zinc mixture. Lead is removed as lead sulfate, which precipitates out for the determination of zinc, or by the process of complexation, that is the use of a complexing reagent. That is, for example, Cu plus 2 plus ion has been complexed with potassium cyanide and therefore the E half is shifted to more negative than potential than lead or cadmium, and thus it can be used for the determination of Cu2 plus. There are three methods which are widely used in practice. In all these methods, oxygen is removed before the polarigram of the solution is taken. So first is what we call it as the wave height concentration plots. Standard solutions of different concentration of ions, they are prepared using a supporting electrolyte and a suppressor. Mostly gelatin has been used as a suppressor or a surface active reagent. The wave heights are then plotted keeping the supporting electrolyte and gelatin above. The polarigram of an unknown is also recorded at a constant temperature. The height of this unknown is referred to as the working curve and its concentration is noted. This is the calibration plot, and then the plot for the unknown solution is taken. The internal standard method. So here the polarigram of the unknown solution, it is taken in a supporting electrolyte and the surface active agent is gelatin, and it is recorded, the polarigram is recorded in and added to the same solution, or a pilot ion is added to it. The only condition here is that the delta of the pilot ion and the unknown ion, it should be differed by zero point 0.4 volt. So the ratio of these two waves is compared with the ratio of some now known amounts of the two ions which has been previously determined. So then the third is the method of standard addition. The polarigram of the unknown is first recorded and then a known amount of standard known solution is added to the same ion and the second polarigram is taken. So the calculations have been made using the equation that is represented in 8.26. The concentration of the unknown is therefore calculated from this. However, sometimes this procedure is not advisable as sometimes high amount or high concentration of unknown species has been recorded. Now, the instrumentation, the basic instrumentation for polarographic analysis has been here shown in figure 8.11. The commonly used polarographic cell, it has an external reference electrode and the itself, it consists here as it is shown in figure 8.11. It consists of two compartments, one containing the solution that to be the studied, that is the unknown, and the other that contains the reference electrode. These compartments, they are separated by a cross member that is mostly a Auger KCl solution, which is held in place by a sintered disc. The second compartment is the solution where DME, that is the dropping mercury electrode, is inserted, and this has N2, the nitrogen inlet and outlet provisions. This simple recording polarogram, it has a potentiometer and a pen recorder, and we also represents also a voltmeter here is attached to it. This is how a basic polarimeter works, and a photograph is shown in figure 8.12. Then coming to amperometric titrations. Now, when we use the Ilkovic equation, that is ID is equal to Kca, the diffusion current is proportional to concentration, keeping all the other factors of the equation constant. So, if the sum of the electroactive material in the solution, it is removed by interaction with some other reagent, let us say EDTA for zinc determination, as it forms a complex with zinc, the diffusion current will diffuse, it will decrease proportionally. Now, from figure 8.13, various common types of amperometric titrations, that is or and A to D dash, they represent the polarograms have been represented here. The figure ABCD, they represent the current versus volume plot, which is the amperometric titration plot, and the A dash, B dash, C dash, and D dash, they represent the current versus applied potential, that is the polarograms for the respective titration plots. So now this is the fundamental principle of a very amperometric titrations, or which are also called as polarographic titration. The diffusion current at an appropriate voltage is measured as a function of the volume of the titrating solution. Now, the endpoint is indicated by the intersection of the two lines after the equivalence point. The voltage which is applied at the beginning of the titration, it must be selected so that the diffusion current to be titrated is obtained. Now, depending on the type of the voltage between DME and reference, the various types of titration curves are obtained. Now, when we look into figure 8.3a, 13a, electroactive material is being removed from the solution by the precipitation or complex formation, that is the zinc versus EDTA method in figure 8.13a. This is the titration curve and amperometric titration curve, and this is the polarogram. So from figure 8.13b, the substance to be determined here, it does not give diffusion current, but the titrant, it gives the current potential. That is, when we titrate sulfate ions in here against lead ions, that is SO4 2 minus is titrated against Pb2 plus ions. So as long as the substance is available, the titrant reacts with the substance and current remains zero. After the substance is completely removed by the reagent, the excess reagent, it gives the diffusion current in proportional to the excess volume added. So here what we get is a reverse L shape. The figure B dash, it represents the corresponding polarogram for this type of titration. In figure 8.13c, we see that the both the substance to be determined and titrating, they give diffusion currents at the particular potential selected. That is, if we talk about the titration of Pb2 plus with Cr2O7 minus, this is the titration curve, and figure C dash, it represents the respective polarogram plot. In figure 8.13d, at the applied potential, the substance gives anodic current and the titrant gives the cathodic current. That is, for example, if we talked about the titration of I minus with mercury nitrate, we get a titration curve. The amperometric titration is shown in figure 8.13d, whereas the respective polarogram here is shown in figure 8.13d dash. So these are some of the various titration curves that can be obtained and that can be used for analysis by from the polarograms or the amperometric titrations. Now the titration cell, it is mostly made up of Pyrex glass. It is a three-necked flat bottom flask in which a microburette DME, that is the electrode, the gas outlet for N2 and an inlet for N2 is provided. The cell is connected to a reference electrode in the form of an attachment with a sintered glass separating from this. The general procedure involves that a known volume of the solution that needs to be estimated is placed inside the titration cell. Required the known volume required for the supporting electrolyte is added and the cell is connected to the terminals of the instrument. Then DO is expelled from the cell by passing nitrogen gas for about 10 to 15 minutes, and then after degassing, the initial current is noted. The known volume of the reagent is then added from a microburette. Nitrogen is again passed for 2 minutes and then is stopped. The current and burette readings are noted at this point of time. This procedure is continuously repeated until sufficient readings are obtained and the graph gives an endpoint at the interaction. So this is a simple polarographic unit and this is the general working procedure for obtaining a polarogram or a amperometric titration. So there are various advantages of amperometry. First, the titration can usually be carried out quite fast and the endpoint is found graphically. A few current measurements here and there and the endpoint are sufficient. So with a few points, determination of endpoint is possible. Titrations can be carried out in cases where the solubility relations are such that the potentiometric or visual indicators are very unsatisfactory. Like, for example, when the reaction is marked soluble, like precipitation or acid base titration, because the readings near the equivalence point have no special significance. The readings are recorded. They are recorded when there is excess of titrate, there is excess of other reagents. A number of amperometric titrations have been carried out at dilutions of 10 to the power minus 4 molar. At many visual or potentiometric titrations do not happen at this much dilute concentration. Foreign salts may frequently be present without interference and are usually added as the supporting electrolyte. So, which is not possible in the case of conductometric titration. The results of the titration, they are independent of the characteristics of the capillary that is used. The temperature need not be known provided it is kept constant during the titration. Although a polarograph is a convenient means of applying a voltage, it is not essential in amperometric titrations. The constant applied voltage may be obtained by just using a very simple potentiometric devices. Then some of few examples of amperometric titration. The first, the most commonly used is the determination of zinc with EDTA. So for this purpose, zinc solution of 0.05 molar is prepared, EDTA of 0.01 molar is needed, and cyclohydroxylamine is also needed. So firstly, during for the procedure, the titrate, it should be 10 times stronger than the iron taken in the cell. That is 5 ml of zinc solution is taken in the titration cell and 1 ml of cyclohexylamine and 19 ml of distilled water was added. The potential was set at minus 1.4 volt versus corresponding to standard calomel electrode. Now this solution is deaerated, that is degassed, and it is titrated with the standard EDTA solution. Nitrogen is passed and the readings of both the burette and the galvanometer are noted down. So initial current will be decreased as the titration proceeds very small value at the equivalence point, and after that it remains constant beyond the equivalence point. So using the correction and plot readings, we can find out the graph as it is shown in figure 8.13a. Now, similarly, for the determination of sulfate with lead nitrate, a potential of minus 1.2 volt corresponding to that of standard calomel electrode is required, and the Pb2 plus is reduced to give diffusion current and is used as a titrant. So, for this purpose, zero point 0.1 molar analytical grade K2SO4 and zero point 0.1 molar lead nitrate solution, ethyl alcohol, concentrated HNO3 and thymol blue indicator is needed. So for this procedure, 25 ml of potassium sulfate is added into the titration cell, 2 to 3 drops of thymol blue indicator and a few drops of concentrated HNO3 is added till a red color is obtained. That is the pH of 1.2. To this, 25 ml of ethanol is added, so which reduces and forms PbSO4 as the precipitate. The reaction here is given in equation 8.27. Then nitrogen gas is passed to remove the oxygen present in the solution, and the DME is connected to the reference electrode. The titration is done with lead nitrate, adding in small volumes, and nitrogen is passed at 1 minute after each dilution. So now we note down the readings for both the burette and the galvanometer after the stopping the passage of nitrogen. The graph is plotted, a reverse L-shaped graph that we showed in figure 8.13b is obtained and the endpoint is detected. Then coming to determination of lead with standard potassium dichromate solution. So the potential selected here is minus 1.0 volt versus the standard calomel electrode at which both the lead ion and dichromate ions they give diffusion current. So the graph obtained will be kind of V-shaped as it is shown previously shown in figure 8.13c. So for this the reagents are required: 0.001 molar lead nitrate of analytical grade, 0.005 molar potassium dichromate, and 0.01 molar of potassium nitrate. So, for the procedure, 25 ml of 0.001 molar lead nitrate solution was taken. 25 ml of potassium nitrate was added as the supporting electrolyte, and nitrogen was passed for 15 minutes. Then, minus 1.0 volt of was set as in the condition in the polarograph. Then 0.005 molar dichromate solution was added from the microburette in zero point 0.5 ml in portion, and nitrogen was passed for 1 minute. So the readings are noted between the burette and the galvanometer after each nitrogen is passed. Initially, the current due to the lead decreases as dichromate is added, and it increases after the end point with excess of dichromate. Now, making the volume corrections and shown as the graph is shown in figure 8.13d, we can find out the unknown concentration of lead nitrate that is supplied to us. Now, next is the titrations with rotating platinum electrode. Since mercury has a limitation that it cannot be used as electrode at positive potentials, so rotating platinum electrode at 600 revolutions per minute have been used. So with platinum as the electrode, steady state diffusion is slow and one has to wait for a considerable time for the platinum to be rotated. So the construction of a rotating platinum electrode here is shown in figure 8.15. So the reagents for using rotating platinum electrode, the determination of antimony with potassium bromate is done. So for this, potassium antimonyl tartarate is taken. 25 ml of this potassium antimonyl tartarate is diluted to 250 ml with hydrochloric acid. Now standard potassium bromate solution is prepared in water, and the potassium antimonate solution, the potassium bromate is added and the voltage is set to zero point 0.2 volt with regards to the standard calomel electrode. The graph is constructed as usual and the concentration of the antimony is calculated from the graph. Next is biamperometry or dead stop end point method. So in amperometry, we use one polarized electrode, which may be DME or solid electrode or metallic electrode like platinum. So here in this potential corresponding to limiting current plateau is fixed and IL is measured as a function of reagent volume. So in the present method of biometry, by amperometry, a pair of identical metallic or like solid microelectrodes are used. This method is very simple and used for the routine and automatic determination of single species. So the instrumental setup has been shown in figure 8.16. The setup is very simple. The here the sim it is the same as that used in amperometry, but here the standard calomel electrode is replaced with platinum electrode in the electrolysis cell and a magnetic stirrer is used. So fixed potential difference, that of known potential difference, is applied between the two electrodes through the adjustment of resistance with a potentiometer. In such potential difference, so what happens is one electrode will function as an anode and the other behaves as a cathode. The shape of the titration curve, it depends on the reversibilities of the oxidation reduction couples at the electrodes, depending on the type of the both the sample and the titrant. So two types of curves are mostly obtained for determination of the endpoint. Figure 1.87 and figure 1.8, we can see two types of curves are obtained. If both the couples, that is the sample and the titrant, they are involved in the titration are reversible in nature, we get the curve corresponding to figure 8.17. So at the end point, the current is almost zero. Like example, in Fe2 plus solution in sulfuric acid medium is titrated with standard Ce4 plus solution. So here the Fe gets converted to Fe3 plus and Ce takes up two ions, that is it is reduced to Ce3 plus. So if the potential difference between the two electrodes is about 0.2 volt, no current will follow. So other examples of such, the during this titration, the current will nearly rise from zero at the mid of the titration to other, and it finally gives a plot like this. So the other examples of such titration, it includes titration of azobenzene in acidic solution. So if one of the couples in the process that we have used is irreversible, then the shape of the curve is different and it is represented in figure 1.18. The example is titration of iodine by thiosulfate. So when this titration occurs, I2 takes up two electrons to form 2I minus, and thiosulfate, it gives up two electrons to form S4O6 2 minus. So when iodine solution, the anode is oxidized to iodide ion, and the cathode it will reduce because iodine couple is reversible. So finally here at the end point, the iodine is completely removed from the solution and the current is nearly zero. So therefore after the end point, the current remains the same because the titrant couple is irreversible and the applied potential value is small. So other examples that involve such type of titrations is titration of azobenzene in dilute HCl with chromium ion. So these are two important cases of biamperometry. So, in summary, we can say we have talked about the theory of polarography and amperometric titrations. We have discussed various aspects of amperometric titrations and the influence of the various types of polarography. We have also talked about biamperometry and known the certain examples of biamperometry. So, with this, we conclude today's class. If there are any questions to ask, please feel free to ask. So if there are no questions, thank you for today.
Thank you, ma'am.